Yeah, the Bukh plays the Toronto was definitely, I think people enjoyed it. Jacob was the first bit of yeah, the Fuji or something, right? Fuji's good. I mean, Brookline is certainly better than Fuji. I don't remember which place in Main Street you might have gone.
It was a good idea. It seems to, I think it should work for it's very cute.
For something.
Yeah.
Okay, so good afternoon. Let's continue. Our next speaker is Boris Bukh, and Boris will some very nice results. Strengths of matrices.
Okay, well, thanks, for chairing the session. It's important to thank the chair of the session first. That's very nice. And of course, the organizers for inviting. Okay, so what I'll tell you is, well, really more of an algebra problem. It's motivated by combinatorial problems, which I will tell you about. So the plan for the talk will be, first I start with a few combinatorial problems, which with the same underlying algebraic difficulty. Then again, I will isolate it algebraic difficulty, and then I tell you what I can tell you about this algebraic problem, which is okay. Some results, but not a full solution. Again, please don't hesitate asking questions. It should be fairly relaxed. Okay, let's start. So as a start, I will talk. Use the following a fairly intuitive problem. It was already mentioned in the problem session. That of equiangular lines. So what's a family of equiangular lines? Just to remind you, this is a family of lines in Euclidean space, all going through the origin, with the property that any two of them meet at the same angle. Okay? And again, so examples. There are pictures in dimension 2 and 3. So dimension 2, you can make two equiangular lines very easily, just anything really. But you can make 3 by taking the regular hexagon and drawing large diagonals. And you're going to get a picture on the left. And it's easy to see it will be the largest you can find. In dimension 3, the best construction turns out to be you start with the regular icosahedron. Again, look at the large diagonals with the principal points, drawing by a line. And again, it's easy to check that this is also a family of equiangular lines. And okay, it's slightly harder, but okay, can be shown that this is the most you can get. Okay. Okay. So this is a fairly intuitive algebraic geometric problem with a strong combinatorial flavor. Okay. Let me basically translate it into algebra. Okay, so I can code the lines by the directional vectors. I mean, they all come from the origin, so I can just pick a direction which it sticks out from the origin, and it can normalize it. So it's, again, I get a unit vector. So I get a bunch of unit vectors, and the condition on the conditions on the angles being the same translates into the condition on the inner products. So so I can look at basically all the inner products. It makes a matrix called Gram matrix. So I have a condition on this matrix. Let's make sure, people following, what will matrix look like? Again, some people are disqualified, like Penny and the people behind. Okay.
What was behind it? Same absolute value.
Yes, same absolute value, exactly. So intuitively, basically, because cosine is not arccosine is not one valued, or conversely, when I choose this vector, I can replace it by an opposite vector. It flips the sign, and this is the only ambiguity there is in the problem. So really, what it will look, diagonals will be 1, okay, because it's a unit vectors, and everything else will be plus minus some number which is called alpha. And really, this is more or less reversible. Again, so if I establish a matrix like this with extra properties, positive, semi-definite, then I can, with a bit of linear algebra, it's easy to see. I can actually make the singular in this unit vectors with which correspond to lines with the angles being the same. Okay, so how do we translate the condition about the number of lines and their dimension? Okay, let's just look at that. So what we have n vectors. We can describe the Gram matrix in the following way. We make a matrix whose columns are these unit vectors, and then the Gram matrix is just the matrix of the inner products. So you just take this matrix, rotate it, and multiply it to what we started with. Okay, that's matrix of inner products. So this matrix, because it's n by d matrix, has got a rank most d. Its height is just d, and so the Gram matrix has a rank at most d, and so this is how the dimension appears in this matrix, and the size of the matrix will be the number of elements. So really, what we're getting is a problem of the following shape, a general shape. The diagonal is constant, and off-diagonal elements are of some, in this case, one or two possible values. And we want to have a matrix which is small rank, so it corresponds to a small dimension of a construction back there, and large size. Again, there's a trade-off, obviously. So I'll call matrices of this general shape LD matrices. Okay, so diagonal is D, all entries are D, and off-diagonal elements are all from set L. So this is LD matrix, and I want to know basically problem for this case. Okay, so I will not be concerned with the positive semi-definiteness in this talk again. So yeah, it is important, for example, for this problem, but again, I want to. This is what I'm looking at. Okay. One thing I want to say right away that if you're doing this generality, you can immediately make a small but useful simplification. We can assume that diagonals are any number you want. In particular, we can assume it's 0. This is simply by subtracting a matrix which just has a constant entries, like just all entries are equal to D. Subtracting this matrix will change the rank by at most 1 because this is a matrix of rank 1. And okay, so the advantage of this case is that of course we have one fewer parameter. I mean, so we just can speak of set L. but more importantly, the problem now became more symmetric. So now problem became dilation invariant. So now if I take a set L and I multiply every entry of L by some scalar, non-zero scalar, then nothing will change. I mean, the rank will not change. Nothing changes really. And that symmetry is useful. It makes things nicer. We lose, of course, that plus minus 1 because now ambiguity. We don't know what exactly the rank of the original thing was. But unfortunately, the results I'm going to show are not precise enough for this plus minus 1 to make a difference. So again, from now on, I will be speaking about L matrices, which is basically matrices where again the diagonal is 0 and off-diagonal entries are in the setup. Okay? That's it. Okay, so let me just give you some other example of where this kind of things arise. I mean, there are more examples. Eigenvalue multiplicity of a number. Okay, so again, so what's the setting? We have okay. If you have a number lambda, so a real number lambda, and if I have a graph G, I can ask myself, what's the multiplicity of lambda as an eigenvalue of this adjacency matrix of this graph? And I can ask you, how big can it be? So there are some classes of graphs for which it's, this kind of multiplicity can be very large. For example, strongly regular graphs are class of examples, graphs where have only two non-trivial eigenvalues, so okay, they will have large multiplicity, for example. But but generally, I ask how large can it drive multiplicity of some eigenvalue of a graph? So this is again a problem of the same flavor. So let's just do the translation. So adjacency matrix of a graph is a 0-1 matrix. It's a matrix 0-1 matrix. So 0 diagonals, 0-1 elsewhere. I'm interested in the eigenvalue multiplicity. So eigenvalue multiplicity, it's the rank of a matrix which is it's a nullity of the matrix which is obtained from original matrix by subtracting negative lambda times identity. So it's this matrix on the right. And by rank nullity theorem, this is really I'm talking about making the rank of this as small as possible. And again, I can now, this is exactly this falls in the general framework. I can add lambda everywhere, and I'm going to get a L matrix for some set L of two elements. And this is reversible. Okay, so this is another example. Let me mention a couple of more examples. We saw Bangal lines, multiplicity graph eigenvalues. For example, if you look at the sets in the Euclidean space with few distinct distances, which is but then really few, like say 2 distances or 3 distances, that's naturally can be cast into this framework. I will not explain how, but it can be. Another kind of setting which is very close to my heart is families of sets with respect to intersection. So let me just briefly explain what those are, because I will mention it later in the talk. So the basic setting is this. You have a family of sets, all of the same size, say each of them is the element set, and there is a condition on their intersection sizes. So maybe, for example, I will say that any 2 of them will either be disjoint or have just one element in common. So this would be something called Steiner system. Or maybe I'll say that any 2 of them will have some intersection in one of the prescribed possible intersection sizes. And again, the question is, how large can such family be? Okay, that's a very basic question. And one way, and probably most basic way of answering this question is you make it that same matrix of made whose columns are characteristic vectors of the sets. So these are vectors for which whose positions are indexed by elements of the ground set, and 1 signifies that element is in the set and 0 signifies that it's not. And then basically again you make the same kind of construction, A transpose A, to the gram matrix of this vectors, and again inner product is just intersection sign. So this matrix will have D's on diagonal, because I just assume this is the element sets, and of diagonal entries will be elements of my set now. So and again, the size of this matrix will be the number of sets in the family, and the rank will be the size of, bounded by the size of the ground set. So again, same problem we are facing. And again, this is exactly how, for example, the famous Frankel-Wilson results on restricted intersections were obtained, like exactly by this kind of, looking at exactly this kind of matrices. And with various applications like proof of work. Okay. Okay, so this is a few examples. There are more examples of where these matrices arise, but hopefully I can convince you. Okay, it might be worth trying to actually understand like what kind of bounds can we get on the size of matrix or L matrix sometimes. Okay, so let me just tell you upper bound. This is the only upper bound. Okay, more or less only upper bound. We know. Again, I'll explain a little bit more about it. So it goes as follows. So if a set L has k elements, then and I also assume basically in all this talk that 0 is not an L, because if 0 is an L, I can make my matrix as large as I want to, having 0 rank. Boring. So if L has any 0 and there's k elements, then the upper bound on the size is approximately a rank to the power k. It's written here as a binomial coefficient, but it's basically a rank to the power k. It's the standard tensor product argument again, which is I find it difficult to figure out whom to attribute it to. It's kind of implicit, but not quite in the work of Kornwinder. Frankel-Wilson is definitely there, and there's some kind of works in between which are different levels of explicitness, so I'm not sure exactly who I should credit this to. But this is, the bound. And this bound is actually sharp, so which is good news. But it's sharp for some sets L. So I can write a set L and I can write a matrix for which this is going to be sharp. Actually, it will be just exactly sharp. It will be just literal equality in this thing. But the issue is I can only write some sets L. It's not like I know it's true for every L that this is bound to sharp. And I will see examples why it's not so. So what I would like to understand is whether we can improve this for if L is not one of the specific sets, because really the only examples in general where we should know this L is sharp, again I'll talk a bit more, is more or less arithmetic progressions. Okay, that's basically more or less the only case where we should know this will be sharp. Okay, I'm exaggerating slightly, but not by much. Okay, good. Any questions about what's going on, or I'm just making small. Okay, so let me tell you. One thing you can do to get the upper bounds which beats this, and this is more or less. Here's a trick. So here's an example, simple example. Look at the 1-3 matrices. So the diagonals is 0, of diagonals is 1-3. So the general bound I just told you tells you that the size of such a matrix will be no more than rank squared. Okay. You can do better than this using a very simple trick. So again, people in the front are shaking their heads. You can just take this Mark II, right? This is a simple. That can only add more linear dependencies between the rows, so the rank can only go down. But if you do that, the resulting matrix will be zeros on diagonals, ones elsewhere, and which is just differs from a rank by rank 1 matrix, so one matrix from the diagonal matrix, from the identity matrix, and that's kind of the full rank. So the rank of this is going to be is going to be at least size minus 1. So in other words, if you other way around, size of this is at most rank plus 1.
It's depending on parity. If it's odd, then the sum.
Yeah, you can. Yeah, exactly. So if you can actually compute the rank easily, if it's odd, it's going to be. Yeah. Okay. Correct. Otherwise, it's full. But yeah, very good. Okay.
So the 2 change to any prime p is the other same result.
Yeah, you can play. So if you have say 2 entries here, say so it's and the difference is difference between them is say so this is an integer set. The difference of them is not 1, and it's reduced. So again, it's actually small. So then you get the same bound linear bound, where r plus 1. So which is again we will count this slightly later. So if you get this is. Let me just make marks back here. Really, so for if entries are integers, basically the only really interesting case is basically when numbers are k and k plus 1 for some k. So, okay, but otherwise it's just boring. Okay, good. Okay, so let me now tell you some results. So basically, there is before I tell you the results, let me just explain what the flavor of those results is. Basically, the flavor is that essentially this is more or less the only thing you can do. Okay, so namely there is this. So generally, okay, you can reduce it modulo prime. Again, if your entries, for example, again aren't integers, again, say maybe they are algebraic numbers, say, okay. So then you can, instead of working in the ring of integers and reducing modulo a prime number, you're going to really work in the appropriate number ring and reduce the modulo prime ideal. But again, it's the same game you're going to be playing. And again, then you'll just use basic. So again, let me tell you the results. This will be first slide that will take some while to explain. Basically, it's characterization of when there is a non-trivial construction. So for which sets L is there a matrix of large size with those entries in that set L. Okay, so let's go slowly for this side. So N is the answer to our question, which namely how big can I make a matrix, rank R at most R, and entries from L. Okay, so this is what we want to know. A set L has elements alpha 1 through alpha k. So k elements. Again, I'm assuming they are non-zero. And then the following is a characterization of when you can actually make a construction. So first entry saying, well, what I mean by making construction, it means that I can make a matrix which is not just slightly non-trivial. So it's nothing, that's it's size not just 1 bigger than the rank, but at least 2 bigger than the rank. Because again, this example which is Snoga pointed out, you need some, non-triviality really means we'll go one beyond. And the second statement is the algebraic condition, explaining why can you do that. And okay, so it's kind of a bit surprising because this is a linear algebra problem, right? I mean, it's about some ranks of some matrices. So you would expect the condition to be some kind of linear condition on the numbers alpha 1, alpha k, which are the allowable entries. Turns out that the condition is not a linear condition; it's a polynomial condition. So, and it says this, that there exists a polynomial in k variables, which is has integer coefficients and is homogeneous, so that if you plug for the variables the entries of L, you get 0, and sum of its coefficients is equal to 1. So if you just relate 1, 1, 1, you should just sum up the coefficients, it's 1. So let me just explain what's the meaning of this thing. First, okay, why you would expect something like this to be true, of course, a posteriori. So first of all, okay, expect some kind of relation. This is already mentioned. The homogeneity is extremely natural because this is a consequence of that dilation and invariance which we have at the beginning. Because if I multiply all my numbers alpha by some constant, nothing should change. So this is exactly why we have a homogeneous polynomial. And finally, this condition over here, this is basically a generalization of coprimality condition. So really, remember we said, okay, there should not exist a prime model which we should be able to reduce things. So this is really when you take this condition and like in full generality, this is what it becomes. So this is really saying, it's like think about Chinese remainder theorem. It says that if you have some co-prime numbers x and y, there is a linear combination, which is one. This is what we call co-prime. This is really some kind of relative of that. Okay. So that's a algebraic statement which says when you can do it. And finally, once you make a non-trivial construction at all, you can make a very non-trivial construction. Namely, you can make a construction where the size of the matrix is a constant factor larger than the rank. And okay, so the statement here is actually slightly stronger. It says actually limit exists. But again, this is actually some kind of superadditivity argument, which is very easy. I mean, limit might be infinite, by the way. Yes, Zach?
Are real numbers?
Very good question, and I'm sure I expected it from you. Okay, the result is true over arbitrary field. Okay, unfortunately, as you probably can expect, I don't have any results for rings.
Okay, but then when you scale them, let's say all of them by c, right? So the second condition with the ones, where don't you have to multiply it also by?
No, I'm scaling the alphas by c, right? If I ask alpha by c, nothing will change. The polynomial, no.
And integer means integer in this field, right?
In integers, yeah, basically, so if I have a field, I mean, there's a 1, and I can, like 1 plus 1 is 2, so there are integers. I mean, there's normal integers,
This limit can be very, very close to 1.
This limit can be, yes, arbitrarily close to 1.
Even if you fix k? Or
If you fix k, I don't think I know how to answer this question. No. Wait a second. Do I know? No, I don't think I know how to answer this question. My guess is no. My guess shouldn't be able to possibly, but I don't know how it works. I don't know how it should. It's a good question. Okay. All right. So this is characterization when you get beyond the complete triviality. So when you can make slightly non-trivial constructions, but of course it's a bit disappointing because there are definitely sets outside of that for which you get a bound like r to the k basically sharp. So it's not just bigger than linear. It's like quadratic, cubic, whatever, name it. So you would like to have a characterization for when this quadratic happens, cubic happens. Again, I don't have a full characterization. I have basically next step up after this. So let me just tell you what the result is. But for this is okay. Questions about this before I state the next thing?
Is the bound of the degree of this polynomial if it exists?
The bounds on the degree of the polynomial. Yes, you'll see the proof of this. You'll see the proof. Basically, if you have now this r here, you get a degree. Okay. It's not the main thing about this result. Actually, it's not a proof. I mean, you'll see it's a joke really. It's the statement. Finding correct statement was the most amount of work, not the proof. Okay.
Just want to give a comment. So if k equals to think about a triangular line, convergent search should be infinity.
So repeat it again.
If k equal to, then you think about alpha 1 alpha 2 a triangular line.
Yes.
Convergent search should be infinity.
Yeah. So limit might be infinite. Yeah. So again,
So
limit might be infinity.
So I think fixed k possible can do something very
No, the limit can be infinite. I mean, this is okay.
The question was how close.
Yeah. So the question was the opposite direction. How close to 1 can it be? And yeah, for 2 I can answer this question, but for general K I cannot answer. Maybe not on the spot at least. Okay, let's move on. And so this is next result. But again, next step up after just barely more than R. This is a condition of superlinearity. So, okay. So again, so I indicated in green the changes from the previous statement. So it's very similar. So first of all, now the first condition says that I can find a matrix which is approximately k times bigger than the rank, where k is the number of entries in L. And once you can find such a big matrix, the polynomial is not just arbitrary polynomial; it's a linear polynomial. So now it's a linear relation between the numbers alpha, which is again now we feel like we're back into linear algebra world. And once that happens, I can find actually very good constructions. So which is not just arbitrary big, not some constants win, but power win. So r to the power 3 powers. I suspect strongly that there should be r squared here, but I'm not able to make requisite constructions.
And even you suspect that it's always an integer power?
I think prefer not to conjecture that. I'm not so sure.
But it might be true.
It might be true, and it might be, for all I know, it might be basically whatever best bound you can get from the reducing modular prime ideal, and then applying the trivial bound. That might be indeed the answer, for all I know. For example, here's an open problem. Like we could start with some prime-sized field. Is the answer always r to the size of this L? Symbolically speaking. So say you're FP, finite field of P elements. Is this quantity here asymptotic to r to the k? Always.
So question.
Probably not, but I don't know.
So you're saying that 3 implies 1.
3 implies 1, yeah, sure.
And so if we have an omega 3 to the omega r to the 3 halves, then by your conjecture, there should also exist an omega r squared.
Yeah, so I mean currently this would be, I would
there's
think
a
so.
gap that you cannot really get anything strictly between 3 halves and square.
Yeah, that would be, because for this, I mean, again, I have some constructions which for some cases give you r squared. If you want, I can describe what I know there. So that's why I feel more confident conjecturing. In general case, for arbitrary k, I feel less confident. I mean, there are some obstacles which I think will appear, which is not happening here. But it's just pure guesswork. Okay, that's a result. Let me tell you a little bit about what goes into the proofs. Oh yes, Benny.
Do you expect a similar statement for higher powers, but that's not...
No, like I said, I'm not so sure. I'm not so sure. Again, I'm really not sure about it. Yeah. Okay. So let me tell you a little bit about the proofs. It's a math conference. Okay. Before that, sorry, I forgot. I wanted to mention this corollary for the graph case. I mean, like the graph multiplicity case. So here, I can't do the full graph case, but I can do diagrams, which is easier case when you don't raise a matrix. It's symmetric, right? They are direct diagrams. In that case, the maximum multiplicity of a number lambda is n over d, where d is a degree of lambda. Well, if lambda is algebraic integer, and if lambda is not algebraic integer, it's trivial to see that there is no matrix like this at all with the lambda and eigenvalue. For graphs, I can prove similar results for when degree of lambda is at most 4. But for general case, again, it's open and again, depending on timing, I might mention what's happening there. Okay, great. But yes, I want to talk about some how proofs go. Okay, so I will show you first of all where does this condition, the polynomial, comes from. Okay, so what I want to show now is how 1 implies 2. How do you get from the non-trivial matrix to this algebraic condition? So what I'll do is I will think about my matrix. Its entries are these alphas, and I'll think of these alphas as variables. So now I have a symbolic matrix, and I will now look at its determinant. So this determinant will be polynomial in those alphas. But of course, if I think when I plug for these alphas, they are actually values, this polynomial must vanish. Okay, because this is a singular matrix. And furthermore, if I take this polynomial and I plug for these variables once, what I will get a determinant of the matrix with zeros and diagonals and ones elsewhere. And again, it's very easy to compute its determinant. It's just that number. It's a simple calculation. And I also know something more. I know that my matrix is not just singular. It's a bit more than just singular. It's got nullity at least 2. So in particular, it means if I take an n-1 by n-1 matrix, submatrix of it, it's also singular. So what I'll do, I'll just delete the last row, last column, and I do the same operation to that matrix. So again, I look at its determinant. So I'll get another polynomial with exactly similar properties. It will vanish at the alpha 1, alpha 2, alpha k, and if plug 1, it will be equal to some different value again, which is just replace n by n-1. And the next thing, I just subtract the two polynomials, right? So of course, in an instance I want to get polynomial homogeneous, before subtracting, I multiply it by one of my variables. That's it. So this n-1 and n-2 cancel. I'm left with whatever minus 1 the appropriate sign, which I can get rid of, say, by squaring. And if I plug alphas, I'm going to get 0, and if I plug 1s, I'm going to get 1. That was the whole proof. Again, it's much more time went to actually finding this thing. Okay, so that's a proof. Let me just comment about how 1 implies 2 for the second theorem. So when we assume that our matrix not just has nullity 2, but has actually quite large nullity, it's, it's much larger than its rank, we can do the same thing. What you're going to get is that, well, these polynomials, they won't just vanish at this point alpha 1, alpha k. They'll vanish to high order. And this is easy fact, because if you think of a determinant as the polynomial in the entries of the matrix, the order of vanishing is the nullity of the matrix. It's again easy thing to show. So if nullity is high, the polynomials are constructed, they are vanished to high order, and so of course this thing I cook up will also vanish at alpha to high order. But remember in the statement, I didn't say that I can find a polynomial vanishing to high order. I promised you I'll find linear polynomial, which is a different thing altogether. So the next result, which I think probably the nicest part of this work, is basically a way to go from this high order vanishing to a linear polynomial vanishing at a point. So here's the statement. It says exactly what you expect it to say. If you have multivariate polynomial vanishing to some higher order at a point, then it is a linear polynomial vanishing at the same point. And furthermore, if a original polynomial had some coefficient equal to 1, then this new thing can also be made to satisfy this condition. This is a generalization really of Gauss's lemma. Let me just basically sketch what happens in the one variable case. So first, this is homogeneous polynomial, so if you just don't worry about homogeneity. what we have? We have, say, a polynomial, say, p, which vanishes at, say, alpha. Okay, this is a single variable polynomial. So just to basically explain what is the generalization of. Vanishing at some point alpha to some order which is bigger than its degree over 2. Okay, so d is a degree of it's a degree of p's. Okay. Then I'm claiming that there is actually a polynomial vanishing at alpha which is linear, and proof is simple. You just take this polynomial, you factor it into its reducible factors. Okay. And then by the there are going to be at least d over 2 factors which will vanish at alpha, and at least one of them will have degree 1, simply because otherwise degree would be too large. Okay, so this is simple. And furthermore, if my polynomial p was monic, so if p is monic, then all the pi's are also monic. This is Gauss's lemma. I mean, we teach it to our undergraduates, right? So really, now if you take this same thing, but you now take the same polynomial in 2 variables, then you will need to replace d over 2 by 2/3 d. However, this proof completely breaks down. I mean, because it's no longer true that that you can factor p and one of the factors will be linear, and you can easily make examples where p is irreducible. So you just there's no way to factor it at all. So the proof strategy again is uses what I think some people call contagious vanishing argument. So again, so what we have is that p vanishes to high order at this point, and using this, we could infer that it must vanish to some somewhat lower order, some larger set. From doing that, we infer that it vanishes to some slightly lower order still, and some larger set still, and we continue until we find that p must vanish on some very nice and large structured set, and then we can actually do something. Okay, I will not explain more. Just again, it will just not realistic, and also with time constraints, and I will want to speak about other things. But this is so again, so people who have seen, say, Bukh-Katz's solution to the distinct distances problem or Bakish theorem are familiar with this kind of iteration.
What? Even the Gauss lemma case, why the integer, what the factors of the integer coefficients? Can't the factors?
Oh, this is the Gauss lemma. Integer polynomial, if you factor introducibles can be and over Q, you can actually make it integer coefficients. This is Gauss lemma. You look at GCD of the coefficients. This is the content. Okay. All right. Yes,
so it's important that p is an integer homogeneous.
Sorry?
It's important that p is an integer.
Well, of course, if it's not, if you just remove the integer, basically, again, it is all trivial polynomial vanishing at alpha, just x minus alpha, right? So this is really the result of I'm sure it can be generalized to other similar situations, but I haven't thought about the most general ways. Okay. Okay, so this is the what allows me to get the linear polynomial in the second theorem, and which is the right thing to get.
So Q is integer here?
Sorry?
So the polynomial Q is an integer?
Yeah, yes, I should have written. Q is an integer polynomial, yes. There is a linear integer polynomial. Thanks. Good. All right, so let's move. Let me explain about how constructions work. So the constructions, okay, I will show you a special case, which is the construction of digraphs with the prescribed eigenvalues. Okay. So this corresponds to the case k equals 2, when you have to just specify 2 of diagonal entries. The general case is use the same idea, just with more bookkeeping. So this is really the key example. Okay, so first of all, let me remind you what the result is. The result was, okay, if I have a number lambda, then I'm interested in the 0, 1 matrices with lambda as an eigenvalue to large multiplicity. So there are two cases. If lambda is not algebraic integer, it's not an eigenvalue of any such matrix. And this is easily to be seen because the eigenvalues of a matrix are roots of its characteristic polynomial. Characteristic polynomial of integer matrix is an integer polynomial, which is monic, so its roots are algebraic integers. Okay, easy. The second of all, if lambda is an algebraic integer and has degree d, it's got d conjugates, which are also algebraic integers, and each of them will be also the eigenvalue of the same matrix and of the same multiplicity. So therefore, each of them cannot be a multiplicity bigger than n over d. Or if you think about it, polynomial to the power of the multiplicity must divide the characteristic. Okay, so the upper bound here is trivial. So the content of this proposition is really for the case where lambda is an algebraic integer in the construction. So this is what I'm going to show. Okay, so what we do, we start with the not with a 0, 1 matrix. So we want to get a 0, 1 matrix at the end, but what we do is we start with an integer matrix, which has lambda as an eigenvalue. So this is easy to do. I mean, we teach to our undergraduates about the companion matrix of an algebraic integer. So if somebody gives you a polynomial, a monic polynomial, then you can just write down a matrix of size, which is the degree of that polynomial, so the characteristic polynomial of this matrix is the polynomial you were given. Okay, this is just explicit thing, very easy. Basically, it looks almost like a diagonal matrix.
And this is the reason you're doing it for diagrams, because it's not symmetric.
Yeah. Correct. Yeah, this is why it's not symmetric. Okay, so I start with this, and then I want to turn it into a 0, 1 matrix. So what I do is I blow this matrix up by tensoring with a large identity matrix. Now, there are two ways to think about tensor products. Well, there's one way to think about tensor products, but there are two sides from which you can look at them. So either you basically you have tensor A and tensor B. Either you take A and you replace entries of A by block matrices, which are copies of B multiplied by that scalar, or you do the other way around. You start with the B and you replace its entries by multiples by A. It's just a question of indexing the elements of the product. But here it will be much more convenient to think of it as I'm taking entries of M and blowing its entries up by identity matrix. So this is how I want to think about my tensor product. So my tensor product is now a block matrix, which blocks are just multiples of the identity matrix, scaled by the respective entries of the matrix M. Okay, so that's it. So now this new matrix has the eigenvalue lambda to multiplicity L, because I just I just blow everything up by factor of L. So what I'll do, I'll take this matrix and I'll fix it up by keeping multiplicity basically the same and changing its entries to 0, 1 entries. And the way I do it is by perturbing each of these blocks by a matrix of small rank. So if I take a matrix and which has lambda as an eigenvalue and multiplicity, I add to it a matrix of some small rank R, the multiplicity will change by at most R. And this is the because rank is subadditive. And I do it for each individual matrix again. So this is And so I will perturb each of them by a matrix of rank, which is approximately the square root of L, which is the L is the size of my identity, matrix size of my block. So the point is, even though I have to do it many times, this many is only constant many, because my M is a fixed matrix I started with. So there are only there are these squared blocks. It's a constant, and it will get absorbed into this big O. So okay, so now my goal is very simple. I have now a multiple of identity matrix, and I want to find some small rank matrix. So if I add to the identity matrix, I'm going to get a 0, 1 matrix. That's it. That's all the game around. So I'll do this. Okay, I'll give a proof by example. So I'll just show you a typical case, and again, you will have to believe me that it generalizes. Okay, so let's see example of how to turn -2 times identity matrix into 0, 1 matrix. Okay, I chose -2 because it's the simplest thing to do, but it's again it does generalize. Okay, so what we were going to do, we're going to take a set of approximately square root L elements, and we're going to look at all 2-element subsets of that set. So this is a family of approximately L squared, approximately L element, because the subset is size square root L, approximately L 2-element sets, and we're going to make this construction I told you towards the beginning of the talk, where I have families of sets, I look at characteristic vectors, and I just make a matrix made of those characteristic vectors. Again, so and then make a gram matrix. So the gram matrix will have for the entries the intersection sizes between the sets. Now this sets are 2-element sets, so the only possible intersection sizes, well, are either 0 or 1. I mean, they're disjoint or share just one element. And so this will be a matrix whose all the entries of the diagonal will be 0, 1, and diagonal will be 2. And its rank will be at most the size of the ground set, which is like square root L or so. And now if I take this matrix and I add to my -2 times identity, this will cancel the diagonal entirely, and the off-diagonal entries will become 0 and 1. So that's exactly what I was seeking. Okay. That's and again, it generalizes. I mean, so if you have some other numbers, not -2, you need to find some kind of slightly different, say, construction of sets, for example. But it's not a big generalization. Okay. Let me just mention to you since what happens for graphs. Again, as Noga remarked.
But this always works for negative, right? So here you use the
positive. It's the same thing, you know.
You can switch.
Yeah, exactly. You can switch. Yeah. And again, in general, again, you can generalize these constructions appropriately, but it's not a rocket science.
Right. It doesn't have to be symmetric.
It doesn't have to be symmetric. It's going to be bipartite graph, and it could be okay. And it's not going to be graph. I mean, there's some algebra, but okay.
Boris, I think you said this, but I missed it. Sorry. You were saying the multiplicity, so you changed the matrix by doing these additions to the blocks. Mm-hmm. What does it do to the multiplicity of?
If I add a rank R matrix, the multiplicity changes by most R. So I added a bunch of square root L rank matrices, and so it changes by some multiple of square root L, and my matrix is size proportional to L.
Right? It cannot go.
Yeah, because the multiplicity of eigenvalue in lambda is the nullity of the matrix, which is the original matrix minus lambda times identity. So, I mean, I'm changing nullity, or I'm changing rank, but most this thing I'm perturbing. Okay. So yeah, so I wanted to mention about what happens for graphs. So for graphs, again, the issue is that matrix has to be symmetric, and so if the companion matrix is not symmetric, and of course you need actually additional condition It's not true that you can get any algebraic number because the eigenvalues of a symmetric real matrix are real numbers. So if a number is not real, I'm not going to get it. But also, if it has a conjugate which is not real, it's also not going to be an eigenvalue of such a thing. So the lambda has to be real, and its all conjugates have to be real. So it's always what's called totally real algebraic integer. So this is the game. If I have totally real algebraic integer, can I make a matrix which this is an eigenvalue of high multiplicity? Well, even better, I can. What's natural to do is to try to find a matrix of size d of eigenvalue lambda, right? But I cannot do that. So again, I cannot start the same way I started before. Even for the 2 by 2 matrices, it's not true. I mean, because it's just easy calculation. Like what is eigenvalue of such thing? Square root of 3 is not eigenvalue of any such thing. It's easy to see. However, you can play the following game. Instead of starting, say, with 2 by 2 matrix with the eigenvalue square root of 3, you can start with a 4 by 4 matrix, this kind of eigenvalue square root of 3 to multiplicity 2. It looks like this. Okay. And turns out it's actually possible, and this kind of plays this kind of games for arbitrary quadratics. More generally, you can ask for which numbers lambda. Is there a matrix which is an integer matrix with multiplicity of numbers as large as possible, it's n over d, call them such lambda is representable. Turns out, unfortunately, that it's not true that every totally algebraic integer is of that form. So there are degree 6 and larger examples for which they are representable, but for degree 4 smaller they're representable. Again, because the examples are very fun. Actually, the Boris's paper is a joy to read. I mean, yes.
Why can't you just do the companion matrix and then the transpose on the other side?
First of all, you want exactly size d. Second, okay, I see what you're saying.
Size 2D.
Huh?
Okay, yeah, to get size 2D.
No. Okay, let me just get it. First, I'm not sure what you. Okay, so I'm not sure exactly what you're proposing.
Or maybe.
Okay, so let me tell you the best thing we know how to do. Okay, this is paper by Kummer, actually very recent. Is that I can make a matrix of size 9D. Actually, if you root these arguments, you can make it push to approximately 4 or 3D. But if it's constant times d, you can make examples, but not too small constant, like 4 or so.
Where lambda would appear with like this.
1, yes, and then again, you can blow it up and you lose a factor of whatever 9, 4, whatever, depending how you blow it. Okay, so that's the story for this. All right. So let me just mention open problems, and then this will be some open problems, and finish this. So as again we mentioned beginnings, for the case of L has 2 elements, size 2, basically, and again the integers. The only interesting case is when it's 2 consecutive integers. Again, there's an upper bound of r plus 1 choose 2, which is independent of L. I mean, this argument, doesn't see what the entries are. And the question is, can you make does the constant in front must depend on L or not? I mean, must it go to 0 when it's constant times r squared? Can it stay constant? I have no idea. I don't know. Yeah. Anything?
No, it just reminds me something of 2 families of sets that crosswise intersect either by r or r plus 1. So there are some results about this.
Okay.
Somehow it
Well,
would
yeah.
say.
That's the other paper.
Yeah, that is right. Yeah.
Oh.
Yeah, so. Yeah, but
Okay.
yeah. I don't think the answer is exactly the same. Somewhat,
No, I mean, again, first and second families definitely fall into the general framework, but
so
I mean, I might have missed some non-construction, but I would be happy to learn about it. I don't think I missed, but okay, I understood it.
So you don't want the matrices to be symmetric, right? So
Yeah, this is just a general thing. Yeah, I mean, like can you? Or I mean, if you always do symmetric, can you prove better upper bound? I mean, I have no idea. I mean, basically. Actually, speaking of upper bound, I mean, can you prove any better upper bounds for example, like even for this easy argument I just told you, that the eigenvalue multiplicity at most n over degree? And no, can you prove n over degree minus a constant? I think I can do minus 1 or 2, but some stupid arguments.
So to get n over d, everything has to be lambda at these conjugates, right?
Yeah, it's basically, yeah. Can you make upper bounds? Not clear. Finally, I mean, like again, can you say something intelligent, but say what happens for a random set L? I mean, like say take numbers 1 through m, and pick a random subset of size half of that m over 2. This is your set L. How big does this function L and LR will be? I mean, best construction I can make, okay, is basically more or less stupid, more or less find the biggest infinite progression or more and use that. And if something like this were the best thing, you presumably should be able to get some somewhat explicit constructions of Ramsey graphs, like the same way with, say, Frankel-Wilson got their constructions. Of course, no, it's not completely explicit because this says we need to enumerate overall subsets of size m. Okay, so depending how much you so it's not completely explicit. It's just reducing your randomness. But presumably, if you have proof of a result like this, probably you can figure out like what the pseudo-randomness condition is.
So you hope that the rank will be very small for random?
Yeah, I would think so. Maybe. I don't know. I mean, it's a hope. I mean, I have no idea. So I do not know how to answer any of those questions. So anyways, let me stop here, and thank you.
For the first question, so what's the best construction?
The best construction is for the first one is just go here. R plus 1 choose 2 over R plus 1 choose 2 is correct. L is okay. Maybe I'm off by 1. If L is 1, yes, that's the best construction. And this basically this is basically the design, the standard system.
Questions? More questions?
So is it easy to show that if there's a polynomial that vanishes on the alpha i's, then you can find the lower rank matrix, like the other direction of what you showed?
Well, yeah, those 3 things were equivalent.
Yeah, but you just showed the proof that 1 implies 2.
Yeah, I didn't show you proof 2 implies 3. I showed you basically a special case of that proof.
The 2 implies 1. Is that easy to see?
No, basically 1 and 3 is okay. So for the first theorem, the fact that 1 and 3 are equivalent is easy. It's just okay. It's just basically you take a matrix and you just block it. Standardized. Block it. So really you need to construct is more or less one example. So the construction from 2 implies 1 or 3. Basically you do what I showed you how you construct these graphs, except now you have k distinct entries rather than 2 distinct entries. So there's some extra algebra involved. Okay, let me just say the following, but it's not hard algebra.
Okay, that's that for the second.
Thank you.
I started writing in September, and then December. I did
Might erase it.
A couple of years ago because they were more
Anyone related to you?
right down.
Anyone in your field?
Well, yeah, we always compare.
That reminds me of something like puzzle or cheese, so that you have this many lines or I don't know, like